student, we'll continue the chapter chemical kinetics. And last time we have seen rate of reaction, average rate of reaction, and instantaneous rate of reaction, and the units of rate of reaction. And now we will start measurement of rate of reaction. Measurement of rate of reaction. The graphical method is in your course because experimental method is very difficult. For experimental method you will have to choose a particular reactant and the product whose concentration you can measure, because it is not very easy to measure concentration of each and every reactant and product because the reactions are going so fast, and sometimes reactants concentration can be measured but not of the product, and so therefore a choice has to be made, and then in a particular unit time you have to measure the concentration. Means after 1 second, then next 1 second, then maybe next 5 seconds or whatever. So it is very difficult to decide. So this is one of the reasons why the experimental methods are not chosen to measure the rate of the reaction. The second thing is that you will have to stop the reaction at a particular instant of time, and at that time you will have to cool the reaction system so much that the reaction becomes almost a standstill. If not a standstill, then the rate of the reaction must be almost negligible, and that is also very difficult to do for each and every chemical compound. And so graphical methods are used which are convenient, and so in your syllabus the graphical methods are there. So you should know the reason why graphical methods are preferred over the experimental method. So for graphical method, if I have a reaction, A is giving you B is reactant, B is your product, then a graph can be plotted between the concentration and time. So concentration and time, that is, you know that rate of reaction is directly proportional. If I talk for this, it is equal to the change in concentration. If average rate of reaction I am talking about, the change in concentration of A upon the total time, and this is in terms of reactant and this is in terms of product. That we have seen in the last class. So this is average rate of reaction. So first I will do for the average rate of the reaction. So this expression is for the average rate of the reaction. For that, if I first I will plot two graphs. One graph will be for the reactant to find out the rate of the reaction in terms of reactant, and the other will be your rate of the reaction you will have to find out in terms of the product. So this is for reactant. If I take, then this is for the product. So as you know that when the reaction will be in progress, we will have some amount of the substance A to start the reaction. So there will be some concentration of A. Okay, so with some higher concentration, that initial concentration that is quite high, and if I take this point here, if I draw this, so this particular point, if I take concentration of A1 means here initial concentration. Okay, So, and with respect to this, the time will be, let me use the scale. With respect to this, the time will be the time. Here the time, it is your T1. This is initial time. So at this time, the concentration of reactant is A1, and when reaction is in progress, its concentration started decreasing, and the say this much as it has decreased. And the reaction may come to standstill also, but there is no further change, but that is not my aim. Now, suppose at this particular time, if I take up this is time T2, which is final time. This is the this is concentration of A, that is final, so A2. So if I talk in terms of this rate of reaction, that is here, so this will be is equal to initial minus, so delta means difference. So the difference means your what? A2 minus A1. Okay, and upon delta T will be what? T2 minus T1. This is your here A1 is greater, you know that A1 concentration of A, initial concentration, A1 is greater than A2. So therefore this is greater, this is smaller. So the net result will be your negative in terms of the reactant. If this concentration is expressed as X1 and this concentration is expressed as X2, then we can also write here this is equal to X2 minus X1 upon T2 minus T1, or delta X upon delta T. Since X1 is greater than X2, therefore this will be negative for the reactant. So this way you can find out average rate of the reaction. Average. Now we'll do for the product. Okay, for product even I do here because already I have done the derivation there. So I do for the product again here. For product, if I take the concentration of the product, so the concentration of the product when the reaction is started will be 0, and then this concentration will start increasing. Actually this curve is obtained this way. So if this point you take, this is initial, but don't take 0, or you take from some point, not from 0, you have measured up from point this. So from here if you take, this is your concentration of B initial, so B1. And the time with respect to this will be T1. At some particular time, let the time this, if I draw the perpendicular, at this time T2, let the concentration of the product B is B2. So this point is your B2 and this is B1. If this is your X2 and this is your X1. So in this case, when we write in terms of product, if we write in terms of the product, here it is delta X upon delta T minus. Now if I write in terms of product, so what I will have, concentration of A2 minus, B2 minus concentration of B1 upon T2 minus T1. Now you know that here concentration of B1 is less, concentration of B initially is less then the concentration at the second point. So B2 is less than B1. So if B2 is less than B1 and B2 is equal to your X2 and B1 is X1, so we will have this expression. And since this is here, so we also have X2 is less than X1. So if this is smaller, this is bigger, so we will have delta X upon delta T but a plus sign. So this way you can find out average rate of the reaction either in terms of reactant or in terms of product. Now the instantaneous rate of reaction. Instantaneous. So I rub this. For instantaneous rate of reaction, when it is instantaneous rate of reaction, it is your dx upon dt. If it is reactant, it is minus. If it is product, or you can write like this, dA dB upon dt. This will be plus. This is instantaneous. Instantaneous means for a very small interval of time. So if I plot a graph, in terms of reactant, same way you can apply to the product as I explained to you in the previous graph. Here will be time and here will be concentration. So we will have to find out the rate of the reaction at a very small instant of the time. So this we can find out if we find out slope of this curve. So the rate of the reaction will be is equal to slope of the curve. So this curve is slope of the curve, and at this point you have to find out, say this point is P. So slope of the curve at point P. So how we can find out? If we draw a tangent a line passing through point P that intersects the time axis y at this point and the concentration axis y at this point. So if I mark these points as I take the same marking what is given in the book, O, and this is B. So slope of the curve you will be finding out at the point P. So this will be slope of tangent. Slope of tangent. Now, the slope of tangent is your here theta. So it is your tan theta. And tan theta is equal to perpendicular upon base. This is perpendicular AO and the base is OB. So what is here? If this is your initial concentration x1 and this is your, this you take final concentration, this as initial concentration. So here it will be your x2 minus x1 and if the time, and here if I take OB, this is, and if this is your T1 and this time is T2, so this difference is delta T and this difference is delta X. So this will be T2 minus T1 is equal to delta X upon delta T. So if we talk in terms of reactant, then this will be negative, and if we talk in terms of product, then this will be positive. So it depends upon what you are considering, the reactant or the product. So this way you can find out, you can measure the rate of the reaction when reaction is average rate of reaction, and then this way the instantaneous rate of the reaction. Now the factors on which the rate of the reaction depends. The first factor is concentration. Factors on which the rate of the reaction depends. Factors for the, or factors on which rate of reaction depends. The first factor is concentration. Higher will be the concentration, faster will be the reaction. So rate of the reaction is directly proportional to the concentration of the reactant. Okay, the reactant will be your what? The substances which are combining of reactants. This is. Then the second factor is contact between the particles. Which particles? The particles which are reactants. So if they are smaller in size, the particles are smaller, then their surface area will be more. surface area will be more, and so the chances of collision will be more, and more they will come in contact, and so faster there will be the reaction. So smaller size. So if they exist in the solution form, then ions will be there. So reaction will be fast. If they are in the gaseous state, still they will be coming in contact because gaseous molecules are not so dense and compact. But if they are in the solid state, reaction will be very, very slow. So faster reaction will be here. So this will be the order of the reaction in the these physical state of the reactant. Now the third factor is physical state of the, this is all I have mentioned to you. Temperature, the next is your temperature. Third factor is a temperature. Rate of the reaction is directly proportional to the temperature in most of the cases. Very rare, some exceptions are there. So higher the temperature, more will be the rate of reaction, and it is found that for every 10 degrees Celsius rise of temperature, the rate of the reaction is doubled or maybe tripled. So this is the important thing that you need to know, that is with the temperature, how this is changing. Then the nature of the reactant, next factor, fourth factor, nature of the reactant. Reactant is ionic or molecular. If reactant is ionic, reaction will be faster. If reactant is molecular, reaction will be slow. Rate of the reaction will be slow. Then effect of catalyst. Effect of catalyst, in catalyst chapter we have done, but again I show you. Catalyst enhances mostly rate of the reaction, but there are some catalysts those decrease the rate of the reaction. So if I plot a graph, this graph we have done, this is suppose your reaction system, and here is your energy, and reaction is A plus B is giving you C plus D. So A plus B are having some amount of energy, they absorb energy and their old bond break, this we have done in the chapter catalyst, and they reach to the activated complex state, EA complex, and then the product is formed. As much energy they have absorbed, they will remove. Either energy will be removed more than what they have absorbed or maybe less than. So this may be up here or down there. So this is your here if I take this difference is activation energy. Activation energy means energy required by reactant. This is for the reactant and this is for the product. Energy required by the reactant to be converted into the product, minimum amount of energy, this much they will be needing, that is activation energy. So this activation energy we get, but if this is without catalyst, this is without a catalyst, no catalyst. But when catalyst is taken, then this peak is reduced, we get here, and this is with catalyst. So time taken by the reactant will be less when catalyst is used, and activation energy will be reduced less, and so in lesser time reactants will be converted into the product. So therefore, there's a catalyst, they affect the rate of the reaction. Then effect of radiation, there are some radioactive reaction or there are some reaction that those take place in the presence of light, like radiation. Next factor, hydrogen and chlorine will not react in dark. In dark there will be no reaction, but if you take diffuse sunlight, reaction will continue. If you take bright sunlight, reaction will be explosive. So this is the impact of radiation. Pressure is also there. Next factor you can take pressure, but this pressure factor is only in case of gases. Higher the pressure, faster will be the reaction. Why? Because gaseous molecules on high pressure will remain in contact more, and so the rate of reaction will be more. So this is here about the measurement of the rate of the reaction and the factors on which rate of the reaction depends. We'll see in the next class now the law of mass action. So till then, bye.